And we start with the discussion of scintillators. Scintillators are important detectors whose properties depend on the choice of material, and the choice of material is extremely wide in contrast to semiconducting detectors, which are dominated by the choice of silicon. Let's do some introduction. We need some definitions so that we understand the basic operation principles of scintillators. First is luminescence. Luminescence is the emission of photons. Photons can be every possible wavelength, visible light, UV, X-ray, after the absorption of energy. Now it turns out that there's a load of mechanisms that lead to luminescence. For example, one can have luminescence from the absorption of light. So that means light is translated into light. That's called photoluminescence. Heat would be thermoluminescence. Sound would be sonoluminescence. Electric energy would be electroluminescence. Mechanical deformation is possible. Chemical reactions. In living organisms, it's called bioluminescence, although it would usually boils down to a chemical reaction. And for ionization radiation, it's called scintillation. So again, the defining principle of, the underlying physical process that causes scintillation, that is the emission of light in the detector, is ionization. But in contrast to collecting the, for example, electron hole pairs or charge carriers, we want to now collect the light signal that comes with the ionization. So there's a different signal, but the same mechanism that produces it. So scintillation is the emission of photons following the excitation of atoms and molecules by radiation. That's exactly what we need in a high energy physics detector. Then we need to tell apart, when we need to discuss fluorescence. Fluorescence is the emission of light by a substance that has absorbed light or any other electromagnetic radiation. Fluorescence is fast. It happens immediately, 10 nanoseconds, typically. This is desired and exploited in constructing scintillation detectors. Phosphorescence is similar to fluorescence, however, it is delayed. It does not happen immediately. We will discuss in the context of organic scintillators a few examples. Typically, that happens if energy is stored in an energy level that can only that can decay to the ground state, or not in leading order. So in suppressed, in forbidden transition or in suppressed transitions, and then the lifetime of that state can be hours, milliseconds, hours, anything. And that is not desired because the emission is not correlated with cannot be correlated with our incident signal. However, the underlying mechanisms are to be described in terms of the atomic levels and the molecular levels, and so are similar. It's electrons jumping around in between the energy levels of atoms, molecules, and compounds. Okay, let's look at the scintillation detector in case you have not seen one. This is the basic concept. There is a scintillation detector, the scintillating material, and is coupled to a light guide, whose name suggests that it shall guide the light towards a photodetector. Here I put a classic. Photomultiplier. There's a photocathode here, and the cathode, the incident the incident photon releases a few electrons. The electrons are accelerated, hit a metal plate, release more electrons, and this process multiplies until at the final anode, a large signal that's hopefully still proportional to the incident signal can be read out. So that's a photomultiplier. It needs a high voltage supply because one needs a larger gradient, one needs a large electrical potential, large electrical field between the various screens here. And then there is an amplifier. Okay, so the light guide is supposed to lead the incident scintillation, the initial scintillation light towards the photocathode. It's not the only thing that it's doing. Typically, the material properties of the scintillator determine the frequency and the wavelength of the light that's produced. That's clear. The photocathode has a sensitivity in a different wavelength spectrum, and typically these two don't match. So you produce light that's outside the sensitivity peak of the photocathode. So the second task of the light guide is to shift the wavelength, and there are various ways how these wavelength shifting properties can be achieved, and we'll discuss a few in the next slides. So the point of the whole system is to convert an ionization signal that leaves an ionizing heat that leaves a scintillation signal via wavelength shifting to eventually an electric signal that we can then read out. Photomultipliers were used in the past. It's a tried and tested technology. The disadvantage is that their operational characteristics depend on the magnetic field, because these electrons, the bouncing electrons, the trajectories of these depend on the magnetic field that can hardly be shielded. Recently, photomultipliers are replaced with silicon detectors. These are then called silicon photomultipliers, or SIPMs. Okay, that was the principal historic example is Rutherford's experiment. In Rutherford's experiment that we discussed, I think, at length, he discovered the atomic nucleus by shooting alpha particles at the gold foil. He used for counting the hits of the beam axis a circular screen coated with zinc sulfide, which is scintillating. It does have a high efficiency, but it does not have a good transparency for its own light, and therefore it is not used nowadays. Let's look at scintillating materials. Plenty of materials are scintillating. Not everything can be used. There are inorganic crystals and organic crystals. With organic crystals, we mean molecules based on carbon. Those molecules need not come in crystal form. They can also come in liquid form, or amorphous, in which case we call them plastic scintillators. So inorganic crystal, for example, lead tungstate is one. Plastic scintillators are very important. And then noble gases. Noble gases can be gases. It depends on the detector application, of course, or liquid. It is oftentimes important to have for calorimetry applications. For example, one wants to stop the particle, and then high density is required. In this case, noble gases would be in the liquid form, which makes them extremely expensive. Liquid xenon, liquid krypton, liquid argon cost by the thousands per kilo. And having ton scale experiments quickly becomes cost prohibitive. Yeah, there are many more special applications like scintillating classes, which I will not discuss. The applications of scintillation detectors are plentiful. They're used for trigger detectors because they are fast. That means they can give a precise timing to otherwise slow detectors. Remember, in drift chambers, we needed an initial measurement that starts the timing of the drift of the electron in the gas. That was when we discussed the gases detectors. Now, a scintillator is a perfect detector to start the clock of the drift of the electron in the gas volume. So that's where they can be used. Or because the timing is so good in time of flight counters. For time of flight counters, you need to measure with high precision, well, the time of flight of different particle species, and hence timing is essential. For calorimeters, because they can the crystal variants and the liquid noble gases have high density and hence very high stopping power, so they can be used for electromagnetic calorimeters. For position detectors, it's interesting that plastic scintillators can be cast in fiber mats, and these fiber mats can be the fibers in those mats can be connected to amplifiers, and then one has position detectors. Yeah, and then there are nuclear physics applications. So this the image, the top right shows a crystal, lead tungstate, for example, lead tungstate sodium iodide, scintillating crystals. At the bottom here, you see a plastic scintillator. These plastic scintillators are about the cheapest detectors that are possible. I mean, everything costs something, but this is essentially not much more complicated than styrofoam. Okay, basic properties. Now, advantages of scintillators are certainly the short rise time. Within nanoseconds, the scintillation takes place. There is sensitivity to the deposited energy, so they can be used for calorimetry. Their construction and operation is usually simple. A plastic scintillator can just be cut, similar for the crystals. They are cheap and reliable. Now, there are disadvantages as well, and all scintillators have these disadvantages to some extent, but whether they are important or not is really depends on the material. For example, the aging is a dangerous and sometimes prohibitive feature of plastic scintillators. Plastic scintillators don't age well, and CMS will be operated for decades, and we cannot afford to replace and to completely take apart and replace the calorimetry very often. That means we can do it once or twice. So plastic scintillators have been used in the CMS hadronic calorimetry, and aging is a concern, although we are within specifications. Radiation damage and cannot be separated from aging. It causes similar degradation. Plastic scintillators aren't very radiation hard. Lead tungstate, the crystal scintillator, isn't, well, it is actually radiation hard until it hits, it's fairly radiation hard, but it has limitations. The lead tungstate crystals in the CMS calorimetry for the sector that's closest to the beam pipe has lost more than 98% of its signal yield. So it's already down to 2% and will therefore be replaced for the high luminosity upgrade in a few years. Now, the key disadvantage of scintillation is the low light output. most of the energy goes into the creation. Most of the energy of the ionizing particle goes into the creation of charge carriers in case the detector is sensitive to it. Only a fraction is scintillation. In combination with the optical readout, I mean the photomultipliers here, it's sensitive to magnetic fields. Now that's a disadvantage that has been solved recently. We can now operate reliably the scintillators with SIPMs. That technology has been established in the last 10 or so years. In terms of materials, many materials show luminescence. That's the fast emission of light. To be useful, one has to accept certain requirements. Of course, the light yield has to be high. There need to be a high efficiency to convert the excitation energy from the ionization process into fluorescent light. There must be an efficient process. That's just a statement that the scintillators must scintillate. And the transparency with respect to the ion fluorescence must be light, must be high, I should say high. That means that once you create the light, it must be possible that it traverses the detector. For crystals, there's not much you can do. It either is or is not. For plastic scintillators, those are usually mixtures of different chemicals. In that case, the transparency can be adjusted within limits. The emission spectrum must be matched to the photodetector. If that's not the case, and usually it isn't, wavelength shifters can help. The refractive index of the scintillator must also be matched to the photomultiplier tube, because otherwise the incident signal gets reflected and does not reach the photomultiplier. And then it needs a short decay constant. It does not help if you light up your detector and it doesn't stop shining. Let's look at the light output. As we said, charged particle creates an ionization signal. Only a few percent of the energy are lost, quote unquote, to the energy deposit in terms of light, so to the scintillation. Most of the signal goes in the ionization. So the emitted light is also usually of lower energy than the deposited energy. That's specifically true for plastic scintillators with plenty of internal energy levels for the electron, because the electron may lose energy without emitting photons at a wavelength that can be recorded. So typically the emitted wavelength has a longer wave. The emitted wavelength is longer than what is relevant for the excitation. The difference is called the Stokes shift. So a Stokes shift is the increase in wavelength or decrease in energy between excitation and emission. Let's look at some mean numbers, because we know it for gaseous detectors, we know it for silicons. The mean energies required to create a photon are comparably high when we think of silicon detectors. For example, anthracene is a commonly used plastic scintillator, 60 EV. Sodium iodide with a little bit of topping is 25 electron volts. And those two, so the crystal sodium iodide and the plastic anthracene, are often used as reference material, because there's so many materials and our memory is weak. We usually just divide by the corresponding values for anthracene. BGO is a compound crystal with 300 electron volts. The advantage here that this is a very high C material, which is an efficient photon absorbers. So in case photons are a priority, this crystal, or electromagnetic interactions are important, this crystal is a tool of choice. The problem with BGO is that it's very sensitive to temperature changes. Okay, so here anthracene, an organic scintillator. BGO is inorganic. Sodium iodide dotted with thallium, that's this example, under UV light shows this nice characteristic bluish color. Table of material properties. Important characteristics are the decay time. That's particularly relevant for colliders. If sodium iodide is also used for dark matter experiments that have a very low count, event count, so a very low rate, and then the decay time is of course less important. For lead tungsten, it's an inorganic crystal. It's the choice for the calorimetry for the CMS experiment. The decay time is 5 to 15 nanoseconds. Bunch spacing of 25 nanoseconds, so is barely okay. It is okay. If there has been a scintillating hit in the detector, you want the signal to be gone once the next hit arrives. So it reduces to 2 to 4, 2 to 5 powers of E, because that's the decay time. That's per decay time, the signal drops by a factor of E, so 2.7. And lead tungsten is comparably fast. Anthracene is also fast. Steelbane is also an organic crystal. Is even faster. Good. So these are the different material properties. Let's look at inorganic scintillators. So let's forget about the plastic now. There are, of course, also different types of inorganic scintillators. Inorganic crystals, for example, glasses, the ones we don't discuss, and noble gases. So let's look at inorganic crystals and noble gases. I think you're old enough to know that life is difficult. The scintillation mechanisms for the different inorganic crystals, glasses and noble gases, are all different. They all have different response times. It means that I cannot go with you through all the details of all the scintillation mechanisms. It's also not important. It's atom physics, and the specifics determine the properties of the detector. But let's look at a few examples. Sodium iodide is an important one. Sodium iodide crystal is the sodium iodide scintillator combines a few key advantages. It is relatively radiation hard. It is not expensive. One disadvantage is that it is that it decays when exposed to water vapor. So this is the image shows a sodium iodide crystal after being exposed to water vapor, and that is just what's in the air. So if you build a beautiful detector, put it together, and then you can watch it decay, unless it's perfectly shielded. Sodium iodide is used plentiful in dark matter experiments, and those dark matter experiments gain the sensitivity from a low background rate. That means you take such a crystal, you operate it cryogenically, and you hunt for dark matter particles that may or may not strike the detector. The difficult thing is to reduce the amount of background radioactivity, and that's why these experiments are put underground, for example, in Gran Sasso. At our institute, we have the CREST and the Cosinus experiment who do this. And it turns out that while sodium iodide is a cheap detector, a cheap material. It's not dramatically complicated to manufacture, and okay, you have to deal with it's called hydrophobic. You have to deal with the water vapor in the air. The main complication comes from the fact that the dark matter experiment must be completely cleanly manufactured. In other words, the most money goes into cleaning the workshop from every atom of radioactive material, like the radon in the air. Everything must be completely cleaned before the piece can be manufactured. Even tiniest impurities of radioactive material will make the detector dysfunctional, and you will only know that once you've put it inside a mountain, because otherwise your background is too high anyway. So that was a bit of an excursus. Other important inorganic crystals are sodium iodide, cesium iodide with different dotants to change the behavior of the transport behavior of potential ionization signal and the scintillating light. Then BGO, we already discussed, it was used in the lab experiments. Lead, then there are many compounds, and the lead tungstate is used in the CMS experiment. The emitted light of inorganic scintillators is in the 400 to 500 or so nanometer regime. Visible light, partially visible. Advantages are high density, these are crystals, short radiation length, they are partially have very high Z, can have very high, very good, very short radiation length, and a comparably high light output. 400% when normalized to anthracene is possible. And those are relatively radiation resistant. BGO is less radiation resistant. However, you can use it for E+ E- colliners where the radiation isn't that dramatic. Disadvantages are that the inorganic scintillators are usually slower, decay times up to a few hundred nanoseconds, and also phosphorescence. Well, not all of them. Lead tungstate has a good decay time. Some are hygroscopic, I discussed this, especially sodium iodide. It just, you cannot touch it, it will just decay. Inorganic crystals feature a band structure. So let's look at the scintillation mechanism. Similar to the semiconductors, we have a conduction band and a valence band, and the dotting accounts for activation levels. The band gaps are 5 to 10 or so. Typical values are 5 to 10 electron volts, which means these guys are isolators. The absorbed energy excites the electron in the conduction band, and the recombination causes the emission of photons, and that's the scintillation light. The appearance of the extra energy levels from the doping accounts for an increase in the transition probability, so it improves the light yield, and a detailed treatment is beyond the scope of the lecture. Electron hole pairs, for example, that are created by the ionization can couple, they can form excitons, so they can oscillate, then later recombine and emit photons. That's part of the scintillation mechanism. The light output of an inorganic crystal is roughly proportional to the incident energy. That's great because it can be used for calorimetry, where you want to measure the energy. So not only count particles, but like measure the energy. Inorganic crystals are also perfect for homogeneous calorimeters, which are usually which are usually used for electromagnetic calorimeters because it's possible to build them with high Z material like a BGO and lead tungstate. BGO was used at the L3 experiment at lab. Lead tungstate is used in CMS. The right plot here shows a CMS equal crystal with a silicon avalanche photon detector. So instead of a photo multiplier, we have a avalanche photodiode. APD means avalanche photodiode. We are going to discuss photodetectors at the end of the lecture. So this is a beautiful crystal. It's lead and tungsten. It's extremely heavy. It's heavy as I mean, it's as heavy as lead, but it's completely transparent. I mean, at some point in our life, we will fly again, I hope. If you take such a crystal with you and put it in the security of the airport, you will have interesting conversations because this thing is completely intransparent. It's metal, but once they take it out, it looks like glass. That's the magic of inorganic crystals. The emission spectra of the various inorganic crystals are shown on this in this plot, the respective axis on the right, and the spectral sensitivity of two typical photomultipliers are shown to the right. So here you have different shapes. These are the emission properties of, for example, BGO here, or sodium iodide here, and those should match the photomultiplier that you use it with. So for example, it's probably a good idea to use sodium iodide with this photomultiplier here because they match. There would be a cesium iodide. Cesium iodide would be a worse choice because there is less of an overlap. Quantitatively, one of the largest applications is CMS calorimetry. I've talked a lot about it. It has these end cap crystals here are roughly 5 times 5 centimeters. So that's a 5 times 5 centimeter crystal. And it's, if I remember right, it's a 45 or 50 centimeter long. You can hold one of these crystals with both hands. With one hand, it's difficult to hold it because it is so heavy. 2.5 times 2.5 and 2.2 times 2.2 centimeter crystals are used in the barrel, and that gives the CMS detector an superior energy resolution for electromagnetic particles. You can see here that the crystals point towards the primary interaction vertex. So this is the assembly of the CMS calorimetry. The only difficult region is so there are two difficult regions. One is between at 1.479. This is the transition between the barrel and the end cap, and here at the end, because the radiation damage here is already at 98 or so %. Okay, let's look next at scintillating noble gases. Not so different, I would say, from the crystals, except that it is either gases or liquid, in either gases or liquid form. Scintillating gases that are used are helium, xenon, krypton, and argon, mostly depending on your budget. Well, maybe not for helium, but xenon, krypton, and argon argon is a comparably cheap gas with comparably high light yield is the best compromise, can therefore be used in calorimetry. For example, the Atlas calorimeter is liquid argon. Liquid krypton can be used and was used for the Na-48 experiment, which is a fixed target experiment. And the liquid krypton calorimeter is extremely expensive, but has a perfect, because of the high C, has a perfectly short radiation length. If it was, it would be used abundantly if it wasn't so expensive. We cannot even afford liquid krypton. We can rent it, use it, and then sell it. So you better not have a leak in your detector, because if that liquid krypton is evaporating, bankrupt. Of course, depends on the collaboration, but it's not a good idea to waste liquid krypton. Xenon is also very expensive. It goes up to 1,000 euro per kilo. Liquid xenon is used in large-scale, multiple-ton dark matter experiments. The fluorescence mechanism in noble gases is purely atomic, so it's simpler to understand, and also means that the lifetime of these processes is very short. So one gets a fast signal, typically 1 nanosecond or so, hence is usable for collider experiments. The emitted light is in the UV range. What happens? We have an ionization, and from the ionization, from the ionized atom, an ionized molecule forms, and by recombining with an electron, a photon is emitted. It need not be ionization. It can also be that the electron is not kicked out, it's just excited. Then an excited molecule forms, and it can de-excite and disassociate and emit photons at a specific wavelength. So one gets a signal at certain wavelength that is very fast. Now one has to deal with that signal. One has to match it to the sensitivity of the readout. It's not it does not have a broad spectrum. These scintillating noble gases have a very narrow spectrum and the emission profile. Now, gases can also be used. Not everything is liquid. One can also operate gases detectors, typically at the room pressure, at the sea level pressure. The signal yield is too low, hence gases detectors based on scintillation of gases are operated under very high pressure, which means it is a design characteristic of the detector. It can be changed, it can be adjusted and optimized. So if it works for a certain application, that is an advantage. The liquid noble gases, I discussed it briefly, are used in direct detection dark matter experiments. We search for dark matter. We hope they recoil at the nuclei, and the recoiling particles create an ionization and a scintillating signal. For example, xenon 100 and xenon 1 ton, the latter uses 3,500 kilograms of liquid xenon. That is many millions worth of liquid xenon. That's sizable. The advantage of the liquid noble gas detectors is that you can not only see the scintillation, one can also record the ionization signal. So here it says a WIMP, that's a weakly interacting massive particle. It's one of the holy grails we are hunting for, because it could be a dark matter candidate. It hits a nuclei somewhere here, it creates an ionization signal and a scintillation signal. we immediately see the scintillation signal because it's light, it traverses the detector at the speed of light, but there's also a delayed signal from the ionization that can be recorded. So these are ton scale experiments that look for rare events, and from those rare events, scintillation and ionization signal are recorded, and that helps suppress the background from radioactive decays or cosmic muons and things like this. Okay, so these were scintillating noble gases. Let's move towards cheaper solutions and the complexities of the real world, organic scintillators. Again, there are three types and many types of organic scintillators. They can come in crystal form. Organics can be liquid, and they can be amorphous, in which case we call them plastic scintillators. We can call all of these plastic scintillators, but it's only fair to call the amorphous ones plastic scintillators. The plot to the right is I believe that's from our institute. There's a coincidence detector using scintillation light from cosmic muons. So we have here 3 scintillators that are coated, 3 waveguides and 3 photomultipliers and a coincidence electronic. If a muon goes from top to bottom, it will hit all 3. We will record 3 signals, and we will know that a cosmic came through. That's like the simplest thing you can do, record a cosmic muon. That principle is used in the cosmic veto, for example, in the Alice detector. The Alice detector is completely wrapped in scintillators to identify cosmic background radiation. Organic scintillators are aromatic hydrocarbon compounds, aromatische Kohlenwasserstoffe. That means they contain benzene, I hope I pronounce this correctly, ring compounds. The scintillation mechanism is because of the transition of electrons between molecular orbits. So it's a complicated process. Organic scintillators, one of the key properties is that they are also fast, few nanoseconds. Few nanoseconds means they can be used for collider experiments. For example, the CMS hadron calorimeter. It's the last detector before the magnet. So here's the magnet, here's the HCAL, the hadronic calorimeter. That's when it was inserted. Uses a specific SESN81. It's a compound plastic scintillator. Its emission peak is at 440 nanometer, in case you want to know. Organic crystals typically consist only of one component. Liquid and plastic scintillators are usually composed of 2 to 3 components. There's a primary scintillator, and then there are secondary scintillators that act as as wavelength shifters towards a longer wavelength. You don't need these in case the readout matches, but it rarely does, and hence the wavelength shifting components can be mixed in. Let's look at the scintillation in these organic materials. Here's a benzene ring. It's defined by an electron configuration that has of large carbon molecules. It has this pi and the sigma orbitals. Organic means it consists of carbon atoms. Benzene is C6H6, and the p orbital contains weakly bound pi electrons. So there is plenty of fine structure from molecular, vibrational, and rotational mode. You see, this is a complex molecule. It has many degrees of freedom. They are shown, the energy levels in this system are shown to the right. The basic principle is that an ionization signal is produced, scintillation begins by exciting an electron to S1, S2, and S3 singlet states. So we are here, the spins of the electrons as they were in the s orbits in the ground state, they are anti-aligned, and then there are radiationless and radiationless drops that account for the wavelength shifting, and finally the fluorescence, so the nanosecond de-excitation from DS1 to the ground state. That's the fluorescence. Now, there is intercrossing with triplet states that have a much longer lifetime because the spins are aligned. And that's why the organic materials often have undesired phosphorescence. This can be milliseconds, for example. So in a collider experiment, it could very well be that you see a dark count from a collision that happened many bunch crossings before. So this component, the phosphorescence component, has to be kept in check. The typical scintillator signal shape follows from these considerations. One has a total signal that's composed of a fast component, a fluorescent light, and then followed by a slow component. At least that's that's the basic principle of the scintillation in organic materials. Let's look briefly at the organic crystals. There are plenty of them. Organic crystals, naphthalene, anthracene, stilbene, and so on and so on. Many of these materials scintillate. The fluorescence is fast, 3 nanoseconds. Anthracene, the reference material, is somewhat slow. Typically, these organic crystals are easy to handle. They are also not very expensive, and they are mechanically strong. Some of them are stilbene, for example, is fairly brittle. Nevertheless, well, one knows this, can be worked around. The disadvantages are because of the crystal structure is an anisotropic light output that depends somewhat on the orientation of the crystal with respect to the incident radiation, an effect that is called channeling. It's rarely limiting, but it is present. Some of the organic crystals are fairly difficult to process, like stilbene, because can easily break. Here you see the absorption profile of, I believe, of anthracene, but it's typical. These are just the typical. This should just highlight a typical multi-resonance absorption profile, and then the emission at slightly higher wavelength. The average difference here is what we call the Stokes shift. Okay, last type of scintillators and very commonly used are organic liquid and plastic scintillators. Important liquid scintillators come in typically they have industrial names like POPOP, DPO, PBD, p-terphenyl, and so on. I collected here the chemical formulas, not that it is very important, because those scintillators come in mixtures of one or several components. Typically, it's just a few grams per liter of solvent. the average distance to the next molecule should be below the emission wavelength. Why is that so? We have a base scintillator, okay? So we have an excitation that comes with the signal. So we have a base scintillator that gets excited. Let's look at the absorption here for PVD. That's a mixture of PVD, P-terphenyl, and POPOP. Let's say we mix these three together. We have a very wide absorption profile over many wavelengths. If the PVD and P-terphenyl is excited, these emit at lower wavelengths. So we Stokes shift here to longer wavelength, at which point the POPOP can absorb and re-emit at even longer wavelength. So if the geometry of the detector allows it, which just is to say that it is large enough, then these transitions between the different scintillators will end up at the longest wavelength, and that we can then match to our photo multiplier tube. So between absorption and emission of the mixture of these compound plastic scintillators, we can go up and down several times, and at the end we will land at an emitted scintillator light at the longest wavelength. The properties of these plastic scintillators are, despite the fact that the reactions here are fairly complicated, is 3 to 4 nanoseconds. Because they are plastic, they are isotropic. They can be put into any form. Also, waveguides can be made from these. They are not very radiation resistant. That's their problem. One cannot use these plastic material close to the beam pipe. It will just be burned away. However, it's easy to produce these and to add additives. So one can test different mixtures and in a very wide range optimize the scintillation properties, the absorption and the emission profile. For the gases, for the liquid, for all the inorganics, that's very difficult. Except for doping, there's very little one can do there. Good. These were the materials. Let's look at the detector assemblies and the photodetectors, because it's not enough to produce the scintillation light. You also need to record it. Light guides, full system, as we've discussed now, consists of scintillator, light guide, and some detector, a photomultiplier, for example. The light guide here has a flat top and a round bottom. It can also be more complicated, like here. This is a more complicated light guide from a large plastic scintillator, and it optimizes the path that the photons travel. If you would make that triangular, you would the photons would travel different distances with respect to where they came from in the scintillator. Now that light guide here corrects that, because the photon that goes through here have a longer path to travel, so the signal from the whole scintillator roughly arrives at the same time. I do not know where this was used, but it seems like a ambitious project to manufacture this light guide at a large scale. Next concept, scintillating fibers. There are different fiber technologies based on the scintillators that we just discussed. Plastic fibers, glass fibers, and capillaries filled with scintillating liquid. Scintillating fibers can be used in calorimeters, in pre-shower detectors, detectors that force an interaction for electromagnetic photons, and position sensitive detectors. Here is an image from a cross section of a scintillating fiber mat with 6 fiber layers. You see these are really tiny, probably a few hundreds of microns fibers. Particle can go through here and produce scintillating light that is guided through the fiber, and one gets a two-dimensional, at least, measurement with a good accuracy. The LHCb experiment upgrades after the long shutdown. After long shutdown 2, so after the before 2026, this is when run 3 starts, the LHCb tracker will upgrade to 12 layers of fiber mats. LHCb is an asymmetric detector. The beam runs here orthogonal, runs through. It is orthogonal to the screen, and the particles that come along with it from the interaction are measured in these fiber mats that are read out with silicon photomultipliers. So these simple fiber mats are actually great tools for special purpose detectors. The plastic fibers are made typically of polystrols, polyvinyl toluol, with a refractive index that allows total reflection. The core is surrounded by a thin sheet of material with a smaller refractive index, and then total refraction happens, and the light can be guided over long distances. Scintillating fibers for the electromagnetic calorimetry of the core experiment are shown here. Is quite like doll's hair. My daughter has a play doll that I think has scintillating fibers on her head. That's exactly what these plastic fibers feel like. It's absolutely nothing special. Can be produced on an industrial scale. The difficulty is the readout, and also you don't want to confuse these fibers. Okay, these are plastic fibers. Now let's turn to photodetectors. We can only give an overview. There are plenty of photodetectors of different size for the different applications. There are the classical photomultipliers. These are shown to the right. They come in all forms and shapes. These are the gigantic ones from the large water tank experiments where neutrino for the measurement of the solar neutrino flux, for example, and smaller ones for scintillators and silicon detectors as well. I will only give a few examples. Photomultipliers we cannot avoid because they have been the only show in town for many years. The photon hits the photocathode, it releases an electron, it hits the first dynode, which are under a linearly falling potential. So that means typically there's a constant electric field that leads to the release of secondary electrons. So we have secondary, tertiary emissions, and as long as there is no saturation, one operates in a linear mode. So the output is proportional to, in a proportional mode, is proportional to the number of incidentally released electrons, and then comes an amplifier that reads signal. The quantum efficiency is the probability that the incident photon actually leads to an emission, and is 10 to 30%, depending on how well the scintillator is matched to the photocathode. These photomultipliers can have many stages, and therefore in principle an arbitrarily high gain. Of course, they will saturate at some point. Typical gains are similar to what we have in gaseous detectors, 10 to the 4 to 10 to the 7. They are large, and charged particles fly through what is essentially vacuum. Hence, there's a big sensitivity to magnetic fields. Magnetic field, maybe it's well known on average, but the detailed magnetic field in the detector is not at all well known. Every metal, cable, pipe, whatnot can change the magnetic field. And hence, you may in your computer simulate the magnetic field and orient the photomultiplier tubes such that they are least affected. But then if somebody else decides to make a cooling pipe close to your photomultipliers, they may not function optimally. And that's in fact what happened. So photomultipliers are replaced by, for example, hybrid photodiodes and avalanche photodiodes, and those are the two that we still discuss. Hybrid photodiodes are interesting. I think the photon hits an optical window, releases an electron that's accelerated in the vacuum and detected with a silicon detector. Here, the impact of the magnetic field can be corrected because they can simply be calibrated. So HBDs avoid the saturation effect, and they allow some position resolution in case that is relevant for the incident photon. Just for a readout of a scintillator, this will not be the case. So these are the HBDs. The last photo detector that we discuss are HBDs, or avalanche photodiodes, or SIPMs, because they combine several of the concepts that appeared in other subdetectors. The HBDs are silicon devices that are operated in the reverse bias mode in the breakdown regime. So what happens? You have an incident photon. The reverse bias voltage is close to the breakdown of the detector. Is close to the breakdown of the diode configuration, which means that the electric field is high enough that secondary electron hole carrier pairs can be produced. So you produce, like with a silicon detector, you produce an electron hole pair, and the electron may interact with the crystals, maybe with the dopant, to produce additional charge carriers, and that can multiply. So we have avalanche formation, and a breakthrough can occur. Hence, the characteristics of the HBD is to ramp the voltage right before the breakthrough, and the photon that's to be detected then triggers that breakthrough via avalanche formation. There's some dead time involved because one has to set back kill the voltage and remove and wait for the removal of the charge carriers. Nevertheless, these are silicon detectors, so this is not limiting. These SIPMs are matrices of so silicon photomultipliers is what we call matrices of avalanche photodiodes, and because of the avalanche formation inside the silicon, the gain is pretty high, 10 to the 5 to 10 to the 7, and because most of the time nothing happens, the power consumption is actually okay. These detectors are so small that they are completely insensitive to magnetic fields, and that's why in the large-scale general-purpose detector, the photomultipliers were all replaced with HBT SIPMs. They are very radiation hard in comparison to photomultipliers. They are silicon detectors. And comparably cheap. The disadvantage is that they have a fairly high rate of dark counts, which means signals that are fake signals. That's what that means. So the dark count rate of an operator that's operated close to the breakdown is of course fairly high. Any stray particle from a cosmic will at low energy may very well trigger an avalanche, and then you get a signal. Okay, these are the HBTs SIPMs. We are at the end. These are the photodetectors. We're almost perfectly on time. This completes the chapter. I have lost my voice again. I will stop the recording and give you a chance.